the string is an integer between 1 and q. So I use this notation q in square brackets to denote integers from 1 to q. And the output of the function is either 0 or 1, so it's a Boolean output. And we also have a computational device that is expected to give a correct output at the end. And it also has access to the input string. So this is this input string in the domain. And we assume that device can query elements of the string using random access. So given index, say 3, it gets output x3. And so we consider two main types of devices, either probabilistic ones, so this is ordinary computers that are additionally allowed to toss a coin, and also quantum ones, so similar as Einar described in his talk, using qubits and similar things. Okay, and the holy grail of most of the computer science is a question: how long would it take for this device to actually solve this problem? So in our case, to compute the value of the function. Okay, so the main problem is if we have this device. So it's very weird, you know. If you ever have seen some code of not very good quality, then you know that it may be very tricky to understand what actually is going on. And to prove a lower bound that works for any arbitrary crazy code that could happen, and that this code has to do something for a long time, it's actually very difficult. And actually not much techniques are known for doing that. And so one of the techniques is to not really look at what the device is doing, but only look at the link of the device with the outer world, so this input, and to see and to detect and see what's going on when the device actually communicates with the input. And the consequence of that is that instead of counting the time complexity, so the number of elementary operations the device requires to solve the problem, we only count the number of queries to the input, and this is called query complexity. So this may be a very loose lower bound. So of course it's a lower bound, because if a device needs to perform k queries, so at least it's clear that it needs k elementary operations. So, but it can be very loose, because it's obvious that just the device can query all the input and then do something inside. So the best you can hope to prove is linear in the number of input variables, but of course you know there are many problems that require exponential time up to that. But yeah, so that's kind of a problem that it's not related to quantum, that we can't really prove good exponential lower bounds on computational problems. And because of that, we can prove only lower bounds that are sublinear. And for simple functions, like say the Earth function. So I guess everyone is familiar with that. We have n Boolean inputs, input variables, and a Boolean output, and the output of the function is 1 if there is at least one 1 in the input. So again, so the algorithm can do crazy things. So we don't really know what it does, but we can make a simple observation. So we can consider either input that consists only of zeros, or we consider input that contains exactly one put somewhere in the form at random, and all other elements zeros. So, and if the algorithm queries less than a third of the input variables, then the probability, it's easy to see that the probability is less than 1/3 that it actually hits that one. And the probability 2/3 when it doesn't hit the one, and it sees no difference between the strings that consist only of zeros and this adversary chosen input string that consists only of 1, 1. Okay, and because of that, we see that the algorithm, no matter what it does, it has to query linear number of input variables. So the randomized query complexity of R is omega of n. Okay, so this is the main motivation, what we are going to consider in the talk. Oh yeah, I forgot. The quantum query complexity of the Earth function is square root of n, so of two constant functions. And this is because so this algorithm does not work. This is exactly like similar to what the Dominic talked today, because you can query the inputs in superposition, and there is like no such notion what input variable has been queried. So this proof actually breaks, and in fact for a good reason, because you can do better with a quantum computer. And we are mostly going to consider lower bounds for quantum theory complexity. Okay, so this presentation is not about definition, rigid definition of quantum computation. So actually we have seen today, won't talk about that. And it is neither about proofs of lower bounds techniques, how they are proved. So it's reasonable because if I'm not talking about how the device computes, so how can I prove a lower bound? And so what this presentation is about is actually about the formulation of these lower bounds, how do they look like, and examples, applications of these lower bound techniques to specific functions. I'm going to consider the adversary technique. It's not the only one, but it's the one that is most rapidly developing now. And the outline is false. We are going to consider two variants of the adversary bound. The first one is a basic adversary, and the second one is a spectral adversary. And for each of them, we consider two examples. Okay, the k-threshold functions, the graph connectivity, the iterated functions, and element distinctness. Okay, so let me start with the basic adversary. Okay, so recall the earth function example that we had before, it's actually about all distinguishing inputs. So we have the negative input that consists of all zeros and a bunch of positive inputs. So the first input there we have 1 over the zeros, then the second bit set to 1, the third bit set to 1, and vice versa, and etc. And we have n of them. Okay, and we see that no randomized algorithm can distinguish all these pairs of inputs in sublinear number of queries. So it can distinguish some of them. So it can distinguish this by querying the first input. It can distinguish some part, but actually it cannot distinguish all of them. And in fact, it won't distinguish even a majority of them. And because if it doesn't distinguish two inputs, then it cannot tell whether it is the input is this one or this one. So it cannot tell whether the value of the function is 0 or 1. Okay, so let us make this a bit more strict. So mathematically, we select subsets x and y of the domain, where all elements in x compute to the value 1. So in this case, all these are in x. And the second subset is y. In this case, it's just reduced to this singleton. And we also define a relation between x and y. So in this case, this edges represent the relation. So in this case, we have like a bipartite graph, a complete bipartite graph, but it need not be complete. So it may be that some positive inputs are not in the relation with the negative inputs. Yeah, we will see further examples. Okay, given all this, we calculate a bunch of quantities. So let us do this for this example. First, we calculate n. This is the minimum over all x, so all positive inputs that we have selected, all x in capital X, of the number of y that are in relation with x. So in this case, if we take any element from x, it is only in relation with y. So in this case, we have value 1. Okay, m prime is defined similarly, but for y's. So for each y in the capital Y, we count the number of x that are in relation with y. In this case, we have only one element in capital Y and n elements in relation with that. So we have n. Okay, then we have two other quantities, L, xj and L prime yj. They are also like similar to each other, like dual images. And for the first one, we calculate a similar thing. So for each x, so for this given x, we calculate the number of y's that are in relation with that, but additionally that are different in the j's position. And similarly for L prime. We calculate the number of x in relation with y that differ from y in the j's position. Okay, so in this case, they are both ones, because if we go from the positive inputs, then we get only one element in the relation, so it's pretty obvious. In the opposite relation, if we have any input and we have a fixed j, say j is 2, then there is only one input, this one, that differ from this input in second position. All other inputs have the same element as this y. So because of that, L prime is also 1. Okay, L max is defined as a product of L xj and L prime yj over all elements that are in relation, and all j such that xj is different from yj. So this technical definition. In this case, it's also 1 because all Lj and L prime yj are equal to 1, so L max also equals 1. And there is a theorem that the value bound is at twist omega of the square root of m times m prime divided by L max. So, as I said, I'm not going to prove this theorem, I'm only going to use it. And in this case, if we just plug everything in, we have m equals to 1, m prime equals to n, L max equals to 1, we get omega of square root of n. So that means that the algorithm that I talked about previously, the order of square root of n algorithm for the wave function, is tight. So you can do better in quantum case. Okay, so let us consider a different example, a bit more involved, that of k-threshold function. So it's similar. We have again a Boolean input, so Boolean string of size length n as input, and it relates to 1 if there are at least k ones in the input. So in particular, there are functions that we saw previously, just one threshold function. Okay. Again, first we define x, capital Y, and the relation. So the capital X consists of all strings of coming weight exactly k. So they are positive, and somehow they are very close to the negative inputs. So that's why we choose them. Okay, for Y, similarly, we take the negative inputs containing the most number of 1, so we take all negative inputs containing exactly k minus 1, 1. Okay, and the relation between x and y is that if x and y differ in exactly one position. So this is an example. So this is, here we have k ones, here is by 1 less, and there is only one position where they differ. So all such pairs are in the relationship, and also you see that not all pairs are in the relationship, just a small fraction of pairs are actually form this relationship. And so we again can do all the math. Okay, for m, the number of elements in y that are in relation with x. So we can get an element from y if we take any of these k ones and flip it to 0. And because of that, the number of y's in relation with x, this m, is k. For y, we can do similar. We can take any of these n minus k plus 1 zeros and turn it into 1. Then we get an element in from capital X that in relation with y. So this we get that it is n minus k plus 1. Okay, similarly, L, xj and L prime yj are both 1s, because by definition an element is in a relation if it differ in one position. So for each y, there is only one element that differ from x or y in that position. That can be in a relationship with it, and if it happens to be in y for x or in x for y, then we get it. So both of these are 1, and we just calculate L max is also 1, and we get that the quantum complexity of the k-threshold function is omega of the square root k times n minus k plus 1. And this is actually also tight. Okay, so these two were quite simple examples, and I would like to give a third example, a bit more involved.
Okay.
Yes.
Does the theorem also hold for promise problems?
You mean partial functions?
Yeah.
Yeah, sure, of course it does. So, for the graph connectivity function, so another example, I will go quickly through it. We have given access to a graph on n vertices. So, for each edge, we can, given by 2 vertices, we can query whether it is present in the graph or not. And given such a function, given such an input, we have to detect whether the graph is connected. So whether from each vertex you can go to another vertex by a path. Okay, so this is a much tricky. So for X, we take all graphs that consist of one huge Hamiltonian cycle. So like this, so the cycle that goes through all the vertices and nothing else. For the negative, we should take a disjoint graph that is somewhat similar to this Hamilton cycle. So we take two cycles, each of ranks at least n divided by 3. And so that they together span all the vertices. So as a vertex, each vertex belongs to exactly one of the two cycles. And the relation is depicted here if this cycle is in relation with these two cycles, if there exist disjoint vertices A, B, C, D, such that these two cycles can be get from this cycle by switching edges A, B, and C, D to B, D, and AC, like this. So again, we choose somehow two cycles that are really close to this cycle, so that it is hard to distinguish them. Okay, so again we can quickly do math. Okay, the number of such two cycles in relation with a large cycle is order of n squared, because you can take as AB any edge of the cycle, and as DC you can take any edge that is sufficiently far from this edge. So and then if you flip like this, then you get two cycles. M prime is similar, also is quadratic. You can take as AC and BD any edges of the in different cycles and then exchange them. So this gives theta of n squared. And so this is why I need so that both of these cycles are large, because I want to be square number, quadratic number of pairs of edges from here and here. And let us consider Lxj and L prime yj. So there are two cases. In the first case, so this is again the number of y's in relation with x that differ in one edge. And this is differently whether this edge belongs to the graph or not. If it belongs to the graph, so assume this is this AB, there are at most n divided by 3 edges that can be, this is the AC, that can be swapped like this, because that this cycle should be sufficiently large. So this means the main thing that it is linear at most. And if it's not an edge, then it is at most 2, because it's not an edge, so it can be this like this AC, or it can be like this BD. So for each non-edge, there are only two ways how you can swap. You can either swap like this, or you can swap this with this and this with this. So at most two cases. So the main reason that is bounded by constant. Okay, similarly, in this case, if there is an edge, then you can take another edge from the another cycle to swap it, and if there is no edge, this is a non-edge, then there are at most 4 cases how you can swap the things, because this D and C should be adjacent to A and B. There are only a constant number of choices. So you can just do all these combinatorics. Then you calculate L max, that is maximum of this product over x and y such that xj differ from yj. And this means then in this case, in one case, it will be at most linear, and in the other case it will be constant, because it is not possible that you get that Lxj and L prime yj are both in this case, because in both of these cases j is an edge of x and j is an edge of y, and if both of these cases are satisfied, then this is not fulfilled. So if this is fulfilled, then either this and this holds, or this and this holds. So the product is at most linear. If you just plug everything in, you get m prime, so n squared times n squared n to 4th, divided by L max is n, so this is n cubed, and you take a square root, you get omega of n to 3 halves. So this is the type how lower bounds for quantum complexity of functions is proved, using the basic adversary method. So this is pretty much how hard it can get. Okay. Now I'm going to talk about the spectral adversary. And again, in the basic adversary we have a relation between positive inputs and negative inputs. So this is actually an example for two thresholds on 3 variables. So these are all positive inputs for two threshold, and these are all negative inputs. And I put a 1 in this matrix if the corresponding elements are in relation, and otherwise I put 0. And when I calculate this L prime xj, and L max, I consider it only such pairs that satisfy that xj is not equal to yj. So I'm not interested in the pairs that such that xj is equal to yj, so I put 0s there. So in this case, so for each j, there are 3 of them, I calculate 3 such matrices. So here I just put gamma times delta 1, and this means that in the matrix I removed all pairs that have the same first element. So I remove this one because they have the first element, this one, and this one. And similarly here I removed this pair because they have 1 in the first position, and also those 2 pairs. Okay. And similarly I do for delta 2 and delta 3. I haven't put them here. Okay. So actually this is something you can do with any matrix. So you can take an arbitrary matrix, and you may consider this as some weights that you put on this edge of. So previously we have only 0 or 1 as a present or non-present, but you can also put some arbitrary weights there. That is a real number, and I do exactly the same procedure. I replace all these entries that have xj equal to yj with zeros. Okay. In this case, another example, gamma times delta 3. I erase these 6 entries. Okay, what do I do next? It turns out that the correct measure of this matrix is the spectral norm. So recall that the spectral norm of a matrix is given as the maximum of this expression. So the spectral norm is also equal to the maximum singular value, or it is the norm of the largest possible norm of an image of a vector having a unit norm. So it's quite well-known concept in mathematics. And the spectral version of the adversary bound is quite simple. I maximize the norm of this matrix gamma, so that consists of all these weights assigned to different pairs. And I have a subject that if I take any j and I perform the operations I performed before, replacing with zeros of the elements such that xj equals to yj, then the norm of the matrix that I get is at most 1. And this holds for all j. And if I have j that satisfies this property, then the spectral norm, if I have a gamma that satisfies these properties for all j, then the spectral norm of gamma is up to a constant factor lower bound on quantum Fourier complexity. So let us consider function. We want to again the R function we've seen before, and again we get a omega square root of n, but this time not using this formula but using these matrices. That's actually, but by the way, it is exactly the same. So we have all ones here. So this is a negative input. These are all positive inputs. And the matrix consists only of 1. So this is a row of row matrix of with n columns. And when I calculate, say, gamma times delta 2, I will replace by zeros all those elements, all those pairs that have the equal second element. So in this case, second element will be equal everywhere except this row. So only one remains here. Everything else is replaced by zeros. And so the spectral norm of this matrix is square root of n. And the spectral norm of this matrix is 1, but it's easy to see that it's independent of by which delta j multiply. So I get that this is most 1. So this gamma satisfies this condition. And I get that this spectral norm, square root of n, is a lower bound of the quantum capacity of. Okay. So the question, what for? Why do we need the spectral adversary if we have such nice basic adversary that we have this, draw this arrows and just count. Now we have the spectrum of matrices that is something very weird. And there are two reasons for that. The first reason is, although basic adversary is easy, intuitive, nice to apply, and so on, but it has an important limitation. And this limitation concerns the function that presents problems involving some kind of search. So in the search, we have an input, and that input calculates to 1 if we find something in it. And something is some small subset C of variables, such that if we know the values of the variables inside the subset, then we can certify. So no matter what values the remaining variables take, we can certify that the value of the function is 1. So it's called a certificate. And the example is, say, the earth function. So if we found 1 in the input, no matter what all other variables are, we know that the value of the function is 1. Similar is subgraph finding. So if we have a graph and we want to find some subgraph in it of small size, then if we find a signed graph, then it's irrelevant what's other edges are in the graph. And so there are many other problems with that kind. And there is a so-called certificate complexity barrier that shows that the basic adversary that we considered before fails to prove anything better than the square root of n times the maximum size of such subset C. So in both cases, like the earth function, the subgraph finding, the collision finding, this is a constant, so basic adversary fails to perform better than omega of square root of n. But that's not good, because we know that quantum query complexity is larger than this square root of n in most cases. This is one reason, and the second reason is that the spectral of the adversary bound is a semi-definite optimization problem. You can, if it has small size, you can feed it into your computer and it spits up an optimal solution. Okay, maybe that's not so important for now. And it also gives an optimal dual, if you know that. It's similar to linear programming. In semi-definite programming, you also obtain a dual. That is a weakness that shows that the gamma that has been found is the best optimal. So no gamma can achieve a better spectral norm with these constraints. And the interesting thing is that the dual can be transformed into a quantum query algorithm with the same complexity. So this means that spectral adversary is tight. That for any function, no matter what function you take, the optimal value of this optimization program is tight. So this is quite interesting because it's specific only to quantum. Like randomized complexity, I don't know anything like that. Okay. And what consequences does it have? So the first example I'm going to talk about is of iterated functions. So this is similar to what Helge talked in his presentation, but it's a bit different because Helge wrote arbitrary gates. I am considered only gates circuits that contain of one gate, one form. So more formally, I have a Boolean function of m variables. Then I define that the first iteration of f is just f itself. And then I define the k+1 iteration inductively from the case iterations of the function. So I take m copies of the k iteration and I give the disjoint variables to them. So in this case, for the first one, I get from 1 to m to the power of k. The second one, I go from m to the power k plus 1 to 2 m to the k, and so on. For the last one, I go the one that ends to m to the power k plus 1. So graphically, we talk something like this. So at the bottom, we have input. Then this function f is calculated, and it gives its output to the next function of the next row. So the first row is done, then the second row is done, then this row also, it gets its inputs, calculates functions, and proceeds it further. And then the output of the whole function is the output of this very top gate. Okay, and so what's the query complexity of such functions? So first I'm going to talk about what's known in randomized settings. Okay, just as an example, if I take f as R of two variables, R is an associative function. So this is just an ordinary R, so it's boring, we already seen it. The next example is not AND. So not AND on two variables. And so if you apply De Morgan rules, then this circuit is equivalent to this one. So alternating ORs and ANDs. And this also can be considered as a two-player game, where the leaves indicate zeros if the first player wins, 0 if the second player wins, and 1 if the first player wins. And then the value of this tree is who has the optimal strategy, if the players do perform the moves alternatively. Okay, in this case it's a bit more interesting. So if we just consider one gate, so one non-AND function, so there are three cases actually. If both inputs are 1, then to calculate this not AND requires two queries, randomly I mean. So because no matter if we query this one or this one, we should query the second one, because we don't know whether the output is 0 or 1. In this case, if there is 0, okay, let's start with this case. If there is both are zeros, this requires one query. You cannot do better than one query, but for one. But if you query any of these two, you get 0, you know the value of non-AND is 1. So, and in this case, it's somewhat in between, 1, 0 and 1, 1. So the best strategy is to toss a coin and query respectively the first or the second variable. If you are lucky, you query the first variable, 0, then you know that the value of the function is 1. If you are not lucky, then you query 1. And then you have to query the second one. And so in the first case it requires one query, in the second case it requires two queries. So on average it requires 1.5 query. And so this is a bad case for one non-AND. These two are better. This is very good and this is somewhat in between. And the observation is that if we have good, so difficult instances of non-ANDs on one level, then it proceeds with 0 on the next level. And zeros give easy instances for the next level. And vice versa. If I have zeros that are very easy, then I have the output 1 and the next level becomes more hard. And so because of that, the randomized square complexity is better than 2 to the power of d. That is just the number of variables. And it's known that the randomized square complexity of this iteration of the not AND function is given by this expression. So it's theta to 1 plus square root of 33 divided by 4 to the power of d.
And that's smaller than 2.
Sorry? Yes, that's smaller than 2. Okay. But if we replace not AND with a majority on 3 elements, then no one knows what the asymptotic behavior of the randomized square complexity. So there are not matching lower and upper bounds. Okay, but even for this simple function, it's not known. Okay, and the situation here is similar because, like, for majority of 3, this means that if we have 2 equal inputs, then the value of the function equal to these 2 inputs. And so we may be lucky to get these 2 inputs correctly. So for each input, we just take 2 at random. If we are lucky, then they will be equal, and we do not have to query the third one. But we may be non-lucky, and these two, say x1 and x2 are different, then we have to query the third one. Okay. And again, because of that, the complexity is better than 3 to the power of d. And but the exact value is not known. That's the main message. Okay. But quantumly, we are suddenly in a wonderland, because we call for each function f, we can calculate its optimal adversary matrix gamma, and we have this dual, and they have some complexity c. Then these matrices, they can be composed like in somewhat similar to what Helger did in his presentation with span programs. So these matrices can be composed to this circuit, that is iterated function, to case iteration of the function f, with complexity c of k. And so this gives optimal quantum pair complexity for any iterated function. So not just for majority on 3 elements, we can take majority on 5 elements, or whatever weird function you just can think of. And this gives a simple algorithm how you can how we got asymptotic behavior of the quantum Fourier complexity of this iterated function. Okay, and I'm going to end with element distinctness. So I'm going to show the spectral adversary for this function, and so this function is not iterated, so it cannot be sent in this way, and is defined like that. We are given a string x consisted of length n, and each element of the string is integer from 1 to q, and the task is to detect whether there exist two a and b, so two equal elements, whether there exist a and b in n that are different and such that xa equals to xb. Okay, in this case, the subset AB is a firm certificate. So if you know two elements that are equal, that no matter what other elements are, you know that the value of the function is 1. Okay, and by certificate complexity barrier, best adversary gives at most square root of n. So we are going to prove using spectral adversary lower bound of omega to n to 3/3. The idea is a bit different. In basic adversary, we have inputs, just individual inputs, and we have a relation between them, and we prove that it's hard to distinguish most of the pairs in the relation. In this case, it's a bit different. We also try to say that something is hard to distinguish, but in this case, we do not look on the individual inputs, we look like on the inputs of the whole bunch of inputs itself. So actually, what I am going to do this is the adversary matrix with columns labeled by negative inputs. So n is just the set of negative inputs, and rows labeled by positive input. And each positive input falls in a block. So PAB is just those positive inputs such that XA equals to XB. So here are all such positive inputs that X1 equals to X2, here such that X1 equals to X3, and so on. And so the idea is that each of these small individual small submatrices, so from PAB to N, is going to mimic the matrix that contains on negative inputs to negative inputs. Okay, so this matrix is very good because you cannot distinguish negative inputs from negative inputs. They're the same thing, you can distinguish them. So here you can distinguish. If you just query A and B, you'll see that yes, A and B is a positive input. So we cannot, of course, we cannot mimic it perfectly, but the idea is to try to mimic S to such good extent as it's possible. Okay, and after I describe how this mimicking works, I'll reduce this to another combinatorial optimization problem that is of different flavor than that for basic adversary. Okay. So let's start with the negative inputs. So I want to mimic, recall, the negative inputs to negative inputs. So I want to describe better what matrices are there. Okay, the first is kind of somewhat physical observation. So imagine you are a physicist and you see if the size of the alphabet is large, then almost all inputs are negative. So if you take one at random, then there will be no collisions inside. So q is large, I mean something like q is greater than n to cubed or n to fifth power, something like that. And the idea is we do not consider just negative inputs because they have correlations between different elements. They are not allowed to be equal. We just replace by all inputs, so all possible inputs. And the individual elements become independent. So for each matrix, this is like going to be negative to negative, and you just replace this negative to all possible inputs of size n. And I'm going to write matrices from here as linear combinations of matrices that are tensor products over individual elements. So for each individual elements I have just from q to q, so the q is the size of the alphabet. And I have a tensor product, so tensor products means that they are independent. So on the first variable I can have one matrix, on the second variable I can have completely different matrices, and they do not disturb each other. Okay, so what matrices do I put in these small squares? Okay, so we have a query algorithm. It would be good to have some intuition about how this querying proceeds. And because of that, it's good to take two matrices, A0 and I. So A0 is a projection of the uniform superposition. So it's 1 over Q times the O1 matrix. So it's a projection on one-dimensional subspace that is given by uniform superposition, like square root of n, 1, 1, 1, 1, and so on. So this corresponds to the case when the variable has not been proved. So there is no correlation between different values of the variable. So each value of the variable in this, each value of this variable is correlated to each another possible value of that variable. And identity corresponds to the case where it has been proved. So this is perfect correlation. All inputs that have value 2, say, in this variable are correlated only with inputs having value 2 in that variable. And they are not correlated with anything else. Everything else is 0. Okay, so this corresponds not correlate, this corresponds to correlate. Okay, but this matrix is not really so good because it is also a projector, it's projector on the whole subspace. But I would like to, it's also contains this A0, but I would like to have two projectors that are orthogonal, because then I can easily combine them and take linear combinations of them. So because of that, I do not take identity, I take another projector, A1 that is projector on the orthogonal complement of the where A0 projects. So it's identity minus A0, that's matrix that looks like this. Okay. So just another statement, we have this form. So negative times negative is a tensor product of on individual elements, and individual elements are defined by ES, capital S, where capital S is an arbitrary subset of the set of our variables. And on each element here, I have either A0 or A1, independence on whether J is in S or J is not in S. So if J is in S, then I put A1 in the corresponding position. If J is not in S, I put A0. Okay, so these are orthogonal projectors. And as I said, ES corresponds to the state of the algorithm where all values of variables in S are known, have been proved. Exactly. So values of variables in S are known. So if I have n equals S and S is given by the second and the fifth variable, then from the point of view of this operator, so the maybe algorithm that is in this state of this projector, it only sees the second and the fifth column. It doesn't really see what is in this way. So it's all these elements outside these two are indistinguishable to that operator. Okay, so I described what negative elements look like. So the positive elements, I haven't yet talked about them. The positive elements, I'm going to impose the constraint that xa equals to xb. And all other elements can be arbitrary, I do not care. And because I want this matrix to mimic this matrix, the number of elements here should better be equal to the number of all elements in Qn. So in order to achieve that, I repeat each input that satisfies this requirement Q times. So the number of inputs satisfy this requirement are Q to the power of n minus 1. If I repeat each just Q times, I get Q to the power of n elements. So these two matrices are square matrices. And so what this matrix can mimic, sorry. And so here I just depict the columns corresponding to A and B. So where in the first matrix, in the positive inputs, they are equal. So this is like Q times repeated 1, 1, Q times repeated 2, 2, so on, Q times repeated Q, Q. And if I have an operator that have A1 here and A0 here, this operator does not see these values. And from its point of view, this set of input strings looks identical to this one. That is a legal one in the negative case. So I just replace all these ones here by the 1, 2 up to Q. And here as well, I replace all 2's by 1, 2 up to Q. So this is just what I would have in the negative inputs. And this is what I have in positive inputs. And they are indistinguishable for this operator. And here it's similar, exactly similar. But if I have A1 on the second element, So the first one is indistinguishable, so A is indistinguishable, and again it looks like this. So, but if I have both of them, then it cannot be mimicked, because if I have E1 times E1, so E1 goes on A and B, then it sees that I have equal elements here, so I cannot fool him. So we have that this matrix, this block, successfully mimics all matrices of this form that are linear combinations over projectors ES, where not excluding those that have such that A and B are inside S. So I just make this formula with the requirement that alpha ABS equals 0 if both A and B are inside S. So then I cannot use it. All others I am free to use. Okay, so now I describe how it mimics, and one thing that remains is the query, this delta operator. Oh, we have this E0 how it looks like, and E1 how it looks like. And assume that we have a delta operator, recall that erases everything that is equal, acting on this variable that has E0 or E1 on it. Then E0 transforms to this matrix, so the diagonal gets erased, and E1 goes to this matrix, also the diagonal is erased. So this matrix is a negative of this matrix. And for simplicity, I'm going to approximate that E0 remains intact under the action of delta, and E1 goes to E0 negative by the action of delta. Okay, so this is what we had on the previous slide. And then if we have a projector ES, so this is a tensor product of E0s or E1s, then I have two cases. If J is not in S, this means that on the J's variable I have E0, so it is left intact. And if I have J inside S, so I have E1 in this corresponding product, then I apply this rule, it goes to minus E0, and what I get actually is a minus E of S minus J. Okay, so this is restated against the spectral version of the adversary bound. And so the question, how do I calculate the norm of this matrix gamma? The idea is that the norm of this matrix is just square root of the norm of this matrix, gamma joint times gamma. That is easy to see, that is equal to this. So it is a linear combination of the same projectors ES, where the coefficient of the projector is given by the sum of squares of the corresponding coefficients in all these submatrices. Yes? And then the norm of the matrix of this matrix is equal to the maximum of those. Okay, and using all this, I reduce to this following optimization problem. So maximize, so this stands for the norm of gamma. I have a square root because when I calculate gamma, a joint times gamma, the norm gets squared. Okay, and I assume that the largest coefficient is at the empty set. So I want to maximize the square root of this expression. And also I have this constraint that gamma times delta j, the norm of gamma times delta j is equals to 1. This is given by this. So this subtraction goes because of applying delta, that S union j goes to S with a negative sign. And so because I have minus here, and they are all squared. For a similar reason why they are squared here. And just sum of all AB's, and it must be at most 1. And this is subject that I had because of this mimicking, so I cannot mimic if A and B is a subset of S, so it must be equal to 0. Now we have such a simpler optimization problem, and it's not hard to actually write a feasible solution to that, given by this expression. So if both A and B are in S, then it is 0 by this expression. Otherwise, I take that alpha ABS equals to this expression 1, so 1 over n, maximum this minus 0. So if S is empty set, then it starts with, this expression in brackets starts with n to 2/3, and with each S it goes 0, 0, and then it hits 0, and then it identical 0. If S is greater than, the size of S is greater than n to the 2/3. So we can quickly check whether this condition is satisfied. Okay, so we may assume that the size of S is at most n to 2/3 because otherwise both this and this are zeros. Okay, so assume that. And the one, n choose 2 changes by at most 1 over n. So n choose 2 is the number of ways to choose A and B. Here, sorry. And 1 over n is the difference here when the size of S changes by 1. So I get this 1 over n here. And if I get this squared, it is 1 over n squared times n choose 2, that is less than 1. And additionally, there is one possible complication is if I have alpha S satisfies this equation and alpha S union J satisfies this equation. So it must be 0 when A and B, S union J contains both A and B, and S doesn't contain both A and B. So this is possible if J equals A or B, and the S contains either A or B. Yeah? So in this case, there are at most n to 2/3 changes. So the J must be equal to A and B, and S must contain A and B, and the size of S by this assumption is most n to 2/3. So we have that many changes by at most n to minus 1/3. N to minus 1/3 is just if I take the maximum value and multiply by 1 over n. And so if I get this squared, multiply by that, I get 1. So I have 1 from here, I have 1 from here. So this is bounded by at most 2. I can rescale if I wish. And the objective value, it's easy to compute that it is omega of n to 2/3. So because the objective, I have S empty set, so this disappears. And I have n squared, n choose 2, approximately n squared expressions where each expression is 1 over n squared times n to 4/3, and if I multiply, I get to n to 4/3. If I take the square root, I get to n to 3/3. Yeah. And okay, final slide. So all this we've seen for element distinctness can be generalized. Say to the following problem: we have some number S1 to Sm of subsets of n of sizes each bounded by a constant. And the problem, again, we're given the same input. And to detect whether there exists a subset such that the elements inside the subsets, the sum of the elements inside the subset is divisible by Q. Okay, you can, for each such problem, you can write a similar optimization problem that can be solved, and it's not notion that this is tight. So the optimal value of this optimization problem. So if we take the dual of that optimization problem we have here, then it can be converted to a quantum algorithm, quantum algorithm. So this is again tight. Okay. So yeah, thank you.
Okay, so what do you think about complexity of K distinctness for K more than 2?
Oh, well, you cannot really apply these techniques here like Weber team. I think that the current upper bound is tight. Yeah, but it will require some more work to actually prove it. Yeah, because the main complication is that in this case we can make this very simplifying assumption that for large Q we just approximate by all negative inputs, and this makes things like really easy. Like in general case, it becomes more complicated. Yeah.
More questions? Thanks. Let's thank all the speakers for coming